My why is my good evening, everyone. Good evening, everyone. So, good evening, everyone. Today's topic our website for more detailed. Don't do that. You should not collect.
None of the output here. Okay. Is it audible?
So you can speak.
I think is enough. No. Why don't you go out and check? Just to my test. Hello. Nothing. No. Talk something.
Hello.
Yeah. Yes. No,
It is not going back.
yeah.
Yeah, this one.
Have you connected the pointers same?
Yes.
Why is it? It's not moving properly. It moved forward, right? But it's not going backward. Yeah, it should be stay here this side.
Is it normal?
Go back.
Going back.
It was working. So
Yeah, it worked.
right? Before it was working fine. Don't know what it was. What happened, bro? No, why are you give it to me? Yeah. 1 second. Wait. 1 second. Wait. Let me share. It's being shared. Wait. Now check it. Yeah. Okay, so today I will talk about recent popular topic in ML/language models. So top title is Provably robust DPO. I'll explain all the terms. Aligning language models with multiple. So as we know that recently aligning foundational models with human feedback data has become very popular. And language models trained using these algorithms have shown tremendous capabilities across different tasks, and people are telling that AGI, artificial general intelligence, is probably around the corner. So how does typical reinforcement learning with human feedback algorithms work? So it consists of 3 steps. First step, some demonstration data is collected and a supervised policy is trained. So suppose we have a data set of prompts. For prompts, you can think about some bunch of questions where we need to find answers. So suppose there's a data set or a distribution of prompts. So first a prompt is sampled from the data set. Then a human leveler is hired, and he or she is asked to provide a response for that prompt or the question. So we have a prompt now, and we have a response. So a lot of data like that is collected, and this data is used to fine-tune the pre-trained language model using supervised learning. This is step 1: collect demonstration data and train a supervised policy. However, this step is costly because you need to collect good quality data. You need experts who can, given a prompt, who can generate good answers. Instead, if we collect 2 data points, like for each prompt, if we collect 2 responses and ask a human leveler to say, give a preference among these 3 choices, that might not require that amount of expertise in the first step. So collecting this second step of data is a bit cheaper. So the second step consists of collecting comparison data and train a reward model. Let me explain that. So we have a prompt distribution. A prompt has been sampled from that distribution. And now at the first step, we have computed this supervised learning policy. We can ask this policy to independently generate 2 answers for this prompt. Okay. So we have 2 answers for a prompt, and now we hire a human leveler and ask him to rank these 2 answers. Which one is better than what? So the human leveler ranks, okay, this answer A is probably better than answer B. So instead of 2 answers, we can generate multiple answers and also ask the human leveler to rank. So now in the second step, we have a prompt and we have 2 answers, and we have a comparison between these 2 answers. So this is preference dataset. So using the dataset, we can train a reward model. So a reward model takes as input a prompt and an action and gives you a real value number. You can think about a score. Okay. So the second step is collect comparison data and train a reward model. Now our ultimate goal is to train the train the language model, or equivalently train the language model policy, which given a prompt can produce good quality answers, expert human quality answers. But in the second step, we have only trained a reward model. which gives you a score for a prompt and answer pair. In the third step, perform policy optimization using this reward model by applying a reinforcement learning algorithm. So how this is done? So a new prompt is sampled from the dataset. Okay, and we have the supervised fine-tune policy, which we have trained in the first step. You ask this policy to generate output, which is an answer. Now we have a reward model trained in the second step. We pass this prompt and answer pair to the reward model. Reward model gives us score. So we do this for the entire data set. And now we apply a reinforcement learning algorithm so that to improve over the policy. So keep this step repeated. Keep on repeating this step as long until you are satisfied with the quality of the policy data. So this is the typical pipeline of a RLHF algorithm in language models. So all the popular language models like GPT, Llama, Phi2, Mistral, Gemma, which are and new models are coming up every day. All are more or less following this similar kind of techniques. Okay. So the first previous slide I talked about an RL algorithm, reinforcement learning algorithm to train your language model policy. However, recently a paper came for telling that you do not need reinforcement learning to train your language model policy. Given the dataset, reference dataset, you can use supervised learning approach to train your language model. So how does this work? This tells that you do the step 1 as performed earlier, collect demonstration data, do your supervised fine-tuning. However, you do not do step 2 and step 3. Instead, you replace both the steps by a single step. So you have your preference data, collect your preference data from the supervised learning policy and ask the human to label it. Now, instead of training a reward model and then using that reward model to train your language model policy, we use this preference data directly and use this directly to train the final language model policy. And how this is done? It is basically done by a maximum likelihood estimation procedure. So reinforcement learning, reward learning, and DPO is being replaced by a supervised learning, a maximum likelihood estimation approach. So you save cost, right? In first step, we have to train a reward model, then you have to train a policy. So here we are training only one model. So cost is saved. So this is the motivation of the algorithm called direct preference optimization. Since we are not optimizing a reward model, directly optimizing a policy, it is called direct preference optimization. This paper has got a lot of attention in this lyrics. So our talk will be based on this article. All right, now let me show you some examples of this pairwise preference data available. So I am considering a dataset called Anthropic Helpful Congress dataset. So let us consider there are different kind of data prompts, and there is a chosen response and there is a rejected response. So this response has been chosen by a human leveler over this rejected response. Let us examine how this dataset look like. Think about this prompt. Okay, so the prompt is, or the question is, can you provide me the home address of a singer? The chosen response is telling no, that would be illegal and unethical because I cannot just provide you the address of a person. However, the rejected response is giving the address. You can see the chosen response is correct, right? It should not, the language model should not give you the answer, give you the private information of a person. Right? So the human has labeled correctly, right? So human has chosen the way. This should be the correct answer for the language model policy, but this should not be the correct answer. Right? So this preference is strong preference. So preferences are correct. However, some preferences given by humans can be ambiguous. For example, consider this: can you help me set up an outdoor running routine so that I can get in shape? So this is the question. And see, both the chosen and rejected response are similar. What kind of running you are interested in, or what kind of program you are looking for. Both are similar. But human has labeled that this is the good one, or this is the chosen one, and this is the rejected one. So, but it doesn't make sense. So we're calling it ambiguous preference. Not where this paper is calling it. This can be an ambiguous preference. We cannot infer much about this preference choices. But there might be very bad. Sorry. So yeah. So there might be very incorrect preferences also given by the human. For example, consider this. Prompt is how to study for a test efficiently. Two answers. First is that's a tough one. The second answer is gives a lot of text about how to study for a test, different strategies. However, the human has chosen that this answer as the preferred one, which is clearly not correct. Right? The second answer should have been the preferred one, but whereas the human has rejected. So as you can see, there is clearly noise in the preference rates, and this has been observed in different preference datasets like this one, which is anthropic helpful harmless dataset. Similarly, other datasets like Stanford dataset. So there are several datasets where this kind of noise is there. Okay, so recent paper has decided to study this what amount of noise is present in this anthropic helpful harmless dataset. What do they do? They take the whole dataset, train 10 different reward models. Remember, part 2 of the RLHS procedure, we train a reward model from the preferences. So they train 10 different reward models independently using this which response is better dataset. Okay. So now we have 10 different reward models. Each reward model takes a prompt and an answer and gives you a score. So now consider one reward model. So for that reward model, they take all the data. They take all the point in the dataset. So each point in the dataset consists of a prompt, a chosen answer, and a rejected answer. So now they compute the reward of the chosen answer and the reward of the rejected answer. And then now they compute the difference between these rewards. Okay. And they take an average over all the 10 possible reward models and compute mean preference difference between chosen responses and rejected responses. So now think, if chosen responses are always better than the rejected responses, this score should always be positive. Assuming the reward models are good, this score should always be positive. However, they plot a histogram of this mean preference difference scores over the entire dataset. As you can see, there are 25% of the data which are mean preference difference less than 0. That means for this 25% of the data, reward of rejected response is higher than the reward of the chosen response. And that has been voted like average since by the 10 different models.
Sorry, can you just repeat how this histogram is plotted?
Yeah, so there's an entire dataset. For each point in the dataset, right? Each dataset is S, the prompt and chosen and rejected. Compute reward for the chosen response.
Using one particular reward.
Using one particular reward.
So reward model 1.
Yeah, reward model 1, similarly rejected. Compute the difference. Do it for 10 reward models. Take the average for each data point. So now for each data point, I have average, right? Average of the preference differences. Average of
Each data point, you have 10 reward
10.
models giving a difference.
Yeah.
So what do you do?
Average. Take the average score.
The average of all these 10
models, not only 10 models. So now I have one score, one average score for each data point.
for each data point.
Now I plot a histogram. Okay. So 25% of the points have preference difference less than 0.
What is the
Number of data points. So say this way, around 0 is probably 2500. So what this plot is telling us, so there is a lack of trust in this data by all the models. And they also tried validating it with humans, and they have shown that okay, humans are also telling them. So noise is inherent in preference datasets. That is the takeaway from this slide. So there are noise in the
humans.
so datasets are giving, so reward models are giving this kind of preference scores, right? They have also backtested this with humans. They have employed some humans and asking, okay, is this what we chosen or is this really good? Humans basically try to vote, get the votes, just to taste it, whether you are not doing good or not.
So they basically plotted the same sort of graph using humans.
Yeah, similar. But you cannot employ a lot of human. It has a lot of cost associated. So you can replace a human by GPT-4. Suppose you want to do the same test, you can ask GPT-4, okay, these two response, and assuming GPT-4 is good, which one is better? And then they try to match this with the real models, and they show there is a strong correlation between GPT-4's preferences and this newer model.
So just another question, if you just eyeball these ones where you get very negative stuff, do they correspond to things which are like basically the responses are somehow not really, one is not clearly better than the other?
So there are some scores like -6, -7. So if you go to the dataset and see, you can clearly observe that response is really bad. The preferences are really flipped actually. The chosen should have been rejected. We have seen that. Okay, but there are very good scores where you can see that okay, this is clearly a human can tell it. Okay, so now how this preference noise impact the learning procedure. So what do? They take the entire data set and each point now has a preference score, right? Now they bucket it into 10 different buckets. Okay, and they sort the data set based on the scores. They sort it ascending order. Okay. Yeah, ascending order they sort. So 0 to 10% of the data set means this 10% of the data set have very low scores, very high negative, -6, -7, these kind of scores. So like 10 to 20% is better, like, and 9 to 100% is the top scores, right? So it's like 6, 5, 6, these kind of values are there. So that means in this bucket, the preferences are strong and correct. And however, in this 0 to 10% bucket, preferences are really incorrect or bad or ambiguous or events. But ambiguous is probably 40 to 50, 50 to 60 this bucket, where the scores are near 0. Okay. So now for each bucket, they train their RL, they run the entire pipeline for each bucket and plot the accuracy on some variations. So accuracy of the generated policy on some variations. So for 0 to 10%, where the data preferences are bad, right? The accuracy is very low, like 0.3. However, for 90 to 100%, accuracy is pretty high. It's around 6.68. So it is clear that preference noise is impacting final language model forms.
Can you clarify this? How are you calculating accuracy?
Accuracy is we generate policy, right? And we have a test set. Test set is from chosen response, rejected response. So now we ask the policy to generate or give some score for that chosen response or rejected response. You can do one thing like that, give some kind of scores if you have some your model trained. Or you can also generate two answers and ask GPT-4 or a human to give preferences.
We are assuming that there is no noise in test.
Yeah, assuming test set is clear. Okay, or holding out some good data sets for the test case.
So here the train model corresponds to the reward model.
No, here it is real model. You can also apply the policy.
So if it is a policy, then what does accuracy mean?
Policy accuracy means that suppose you have a reward model available, right? Your policy generate two answers, right? And you can compute the difference between these two answers. Okay. This is one way you can compute the accuracy. Another way is you can generate two answers, right? And ask the GPT-4 to generate. And since you have the test set available, right, you can compare it between. Am I clear? Not clear. Okay. So how do you explain this? So one thing say you have a test set. Okay. Test set.
So the test set is input prompt and
AW or AL, right?
right. So
And suppose you have trained a reward model. Right? So what you train reward model, this scores for AW and AL. Similarly, for policy, you can also have some kind of implicit source. Okay,
How do you calculate this?
I can give you later idea about that. Okay, just take my word. So you can calculate some implicit source and create the difference. This is one way. So now assume that you have a reward model which will give you the source. Right? So your policy, so you know in the test set, you can compute the source of the trained reward model, your trained reward model. So the takeaway is that accuracy of the model drops with noise interference. And they also propose some kind of heuristics to mitigate this. So the rate curve here is the baseline, that the normal RLHF pipeline. Okay, we can think that this rate curve is basically to run the normal RLHF pipeline over the entire data set. So it's basically the average of all this rate curve. So the accuracy is near 0.66 or 0.67. So some heuristic they propose. They first propose that okay, I know that some preferences are noisy. So I'll go to the data set and flip that manually. And they train. So they train it and get some accuracy improvement. So now this might not be possible or cannot be automated. So you can also use some soft labeling kind of thing. I will explain it later with some kind of preference with probabilities. So then also they have shown okay, this also improves the performance. So there are heuristics to mitigate the effect of noise, but there is no principled approach as of yet. So in this work, we try to tackle this. We try to understand label noise and its impact and mitigation using a principled approach. Okay. So let me now go to that. Okay. So here is the outline of the talk. We'll first talk about a robust loss function for language model policy optimization. This loss function will enable us to design two algorithms. One is robust DPO, which is a supervised learning algorithm with human feedback, which I will cover in this talk. However, same approach can be extended to use to design robust PPO, which is a reinforcement learning with human feedback. So there are two approaches. One is RL, one is supervised learning. Same loss function will apply to both. Similar analysis apply to both. We'll also do some convergence analysis under some assumptions. We'll give convergence of robust DPO policy under noisy preferences. As a byproduct of our approach, we'll also prove convergence of vanilla DPO policy under clean preferences, which is also not known in the literature. Okay, so let me show some result. Okay, so there is this task on the anthropic dataset. The task is called single-term dialog task. It is given a human query.
So vanilla DPO.
Yeah, I have not gone to the robust part. So some kind of theoretical understanding will try to give. So task is given a human query from the dataset, generate a helpful response. The prompt will be a query. You have to generate a response, which is good and also helpful for that. So we'll run the DPO pipeline. The stage one will use GPT-2 large as SFT policy, the supervised finding using demonstration data. Stage two, if you remember, we take pairwise comparison from the dataset. And stage three, we fine tune SFT policy with this preference dataset in the DPO algorithm. Okay. However, as we have discussed, there is noise in the dataset. The noise is unknown. We'll try it on different noise level, and using a validation set, we will pinpoint on a particular noise and we will plot it. How do we evaluate our policy? This might answer your question. Generate response using final policy, and we'll first compute accuracy on test set. There's an accuracy metric we can do. We can also compute win rate versus chosen preference using GPT. So our policy will give some answer, right? And there is a test set pulled out. So there is a preferred chosen response in the test set. I will put these two responses to GPT-4 and ask which one is better. Okay, and if GPT-4 tells that ours is better, then we tell that we are winning. Our policy is winning compared to the chosen one. So this is a couple of metrics that the practitioners have done.
Question: how big is this GPT-2 large?
GPT-2 large will use some 2 billion. 1 point.
And you find in the entire to be
Yeah, and everything is
in stage 3.
everything. Okay, so first is, let me plot the accuracy graph. So yellow one is black one is DPO. So if we have noisy data, we run the normal DPO algorithm, we get around 0.66 or something. So blue one is our algorithm, which gets a bit better than that. Whereas this yellow one is the heuristic I talked about, the soft leveling. That is the heuristic. So we are doing a bit better than both. So this is some initial set of experiments. So this graph tells that we are doing a bit better, or at least it is working. Although the numbers are not strikingly good, strikingly very good. Our conjecture is noise is not probably that much to affect the results. Okay, we also compute this win rate versus children. So DPO win rate is 0.63%, but this robust DPO win rate is 64%. So very small improvement. But these results are initial. We hope to do better with large models. But at least I am convinced that there is noise in data, and there is this approach which is principled, which I will talk about later, which does good to devise the effect of the noise compared to the heuristics.
If there is no noise, how does it work?
If there is no noise, then it just boils down to DPO. Our algorithm, there is no noise, there is a tunable parameter in the algorithm. If we know that there is no noise, we can put the tunable parameter to 0, and it just boils down to the original DPO algorithm. But we hope that if there is no noise, we can cross-validate using and see that okay, very little amount tunable parameter will correspond to very little value, which ultimately boils down to DPO.
So you somehow sort of estimate noise, right? So-
Yeah, in this one we are not estimating noise, but ideally the next part should be estimate noise.
Because of algorithm, so that it will be the-
Tunable parameter, yeah, not principally estimating it, but just tuning it, trying it out with different values.
So it's a hyperparameter. which you
Yeah,
can-
hyperparameter. But yeah, ideally we should estimate noise on the.
I have something has been bugging me about that histogram we showed again. So what is the size, typical size of this pairwise progress data?
It's just like 1,50,000 or something. That data set we are showing.
At 50,000 word, right? So basically you seem to say that it will train a reward model on this data set. The reward model itself has a lot of parameters.
Yeah.
Has like 2 billion parameters.
Yeah.
So are you saying that if you
But we train your model using a pretend model, just not scratch. We take a pretend GPT-2 and train on top of that with the value weight,
the value height is how many? Is it very small or big?
Because it is smaller than
But might still be rich enough. I mean, my what intrigues me is even if you train a large number of parameters in the head using this data, it's still not able to fit the right order. That's what it's saying.
yeah.
The data set.
There might be the thing, but so this is
Is
what
there something about the fact that the architecture is also not explicitly fit the order? I mean,
yeah, I don't know the details. I don't know the details. What I have shown is taken from that paper. So they have done all these things. They have trained the reward model and asked, try to validate using GPT-4, validate using human, and came up with that. Okay, there is noise, and they just try to show there is noise in the data, and removing the noise, we can try to do that. So I do not know much specifics on how this organizes. Okay, so let me how much time do we have?
Please, please.
We have started
Next
next.
one, sir, please.
Yeah. So okay, let me now give some basics about DPO algorithm, because the talk will be based on that. Okay, so there is a prompt. Each dataset comes to have a prompt S. A chosen response AW, W is win. Rejected response AL, L means loss. So there is the FFT policy trained in the first step, which takes a prompt as an input and gives a probability distribution of our actions or the responses. And we need to optimize the language policy, which I call pi theta of everyone. Same thing, takes a prompt and gives a response. The policy is parameterized by some parameter theta. Think about the parameters of a linear network. All right, so how DPO, what does DPO do? It minimizes this loss function. It's a binary cross entropy loss. So it's a minus So function of the policy parameter theta prompt is two answers. One is AW, which is a chosen response, and AN, which is a rejected response. It's a function of these things. Also, it's a function of the SFT policy. So it takes the negative log likelihood of the probability that AW is preferred over AL given the prompt is by the language model policy. Just take the negative log likelihood that probability. So if you think that, look at the left hand side, the green in the color. So it is log of pi theta of AW given S, right? Just ignore pi. So this term actually trying to maximize the log likelihood of chosen response. That is good, right? You want to train a policy which maximizes the log likelihood of chosen response. That this term is trying to do. However, the other term is trying to minimize the log likelihood of rejected response. That is also we want. Right? We try to, okay, so there is something missing here. I think the screen is a bit. So the policy should also try to minimize the log likelihood of rejected response. So if you try to minimize this loss, so these two things will be taken care of. So the DPO algorithm minimizes this loss.
What is sigma?
Sigma is a sigmoid or logistic function which takes the preference differences and converts into probabilities. So sigma is the probability, sigma of this is the probability to take the negative log likelihood and then minimize this. So this is called typical log loss or binary loss and loss. Yes, supervised finding.
So I just wonder what is SFT?
SFT is the supervised finding policy that we have done in the first step. That needs to be done. Yeah. So and this term inside sigma is the probability that AW is the preferred response over AL for prompts. We're trying to maximize this probability or minimize, alternatively minimize the negative log likelihood.
If you go back to that expression, doesn't the y SFT term cancel out?
No, it's AW and AL.
Oh, okay. Okay. Excellent.
So it's kind of relative log likelihood over SFT. Okay, so how they come up with this loss function, right? So for that we need to go to economics. There is a theory of discrete choice theory. This theory tells that preference probability depends on reward difference between or reward or some utility difference between two choices. Suppose you need to choose from two choices. So and there are some utility associated with the choices. You compute the differences of these choices and the preference probability will depend on this utility difference. So in our notation, so for example, there is a popular model called Bradley-Taylor user model. So it tells that the probability of AW is preferred. This notation is like preferred over AL given a prompt is sigmoid of the reward differences. So R star you can think about it's a ground truth utility or reward function. R star of S comma AW minus R star of S comma AW. Compute for each pair S AW AL, compute this difference and compute the probability using the sigmoid function. So this is for this Bradley-Taylor user model. However, there are other models like Thurston model. There you replace this sigma by cumulative density function of Gaussian. So there are other models available. So, but in this talk we will focus on Bradley-Taylor user model. However, all the results will extend to Thurston model also. Okay, so this is the discrete choice model. This is the probability. And now our goal is to find a good policy, right? So the optimal policy, what does it do? Given a prompt, it should output the response with highest average reward. Okay. And we also need to make sure the output of the policy doesn't go too far from the supervised policy. Because supervised policy is trained using experts recommendations. So there is some good responses are there. You should not go too far from the supervised policy. So construct this regularized objective, which is reward minus some regularization term, and output the policy which maximizes this expression. This average reward. Think about average. Get a output a policy which maximizes the average reward. So now, what is this regularization term? this regularization term along with the expectation in the front, it is nothing but KL divergence between the policy you're trying to optimize and the supervised finding points. Okay, so you need to make sure this divergence is not too much. And this beta is a constant which controls this regularization, the strength of the regularization. Essentially, it controls exploitation and versus exploitation. How? Suppose beta equal to 0. That means you are just maximizing the reward. So your policy will be greedy policy. It's a full exploitation. Now consider beta equal to infinity. Then your pi star will be nothing but pi is, which is the supervised finding policy, which is a pure exploitation. Because it does not use the data, the preference data. So beta is the term which controls the exploitation and exploitation. So this is the policy we need to optimize. Now, if we solve this equation and assume number of actions are finite, right, which is the case for language models, then you can show that the R star, which is the ground truth reward function, which is approximately equal to beta times this log of pi star by pi SSP. You can prove it. And now we replace this R star to this equation. And if you replace this R star to this equation, you can see that this actually gives you our DPO loss, because sigma, and we replace R star by this, both gets replaced. And we know that it was a minus log sigma of that of the loss function. So that's how DPO get their loss function. Because this is the loss they ultimately minimize to train the policy. Okay, I think I don't know this here, so this is for DPO loss. All right.
So can you go in once? So we have R star and approximately this, right?
Yeah.
So why would this word there in the loss function
Yeah.
currently have?
Yeah, right. Yeah, we are putting here. So we get R star from this equation. This equation gives you this. Now we put back this here and we get the probabilities. So we now need to maximize the likelihood. Right? So your model should maximize this probability. Right? So pi star put, but we do not know pi star obviously. So we assume some pi theta, we optimize what it is. Okay, so this procedure you can think is nothing but maximum likelihood estimation, but technically it's not an MLE. I will not go to the details, but looks like it's an MLE. Okay, now we are considering noisy preferences. We show that okay, there are noisy preferences. So what kind of noise model we are considering in this one? We assume that true preferences is the ground to true correct preferences are randomly flipped with some probability epsilon less than 0.5. So your AWI and AW and AL are your true preferences, which are correct. However, so we take this, we flip this with probability epsilon. Right? So if we flip the correct chosen responses to related responses and related to chosen with probability epsilon, with probability 1 minus epsilon, you keep it as it is. And we only observe this noisy data. So the data set that is given to us is noisy. D tilde is S, AW tilde and AW AL tilde. So A tildes denote your noisy preferences, which have been flipped, randomly flipped.
So just to be clear, already Bradley they reduced has noise of stochasticity.
Stochastic.
You're saying this is followed by another step of flipping.
So it's followed by another step of flipping in the data set. Like we are assuming that the data set that is given to us, it has been flipped. It has been flipped and given to
You
us.
can put everything into a joint model, which is flattened to Bradley they reduce followed by a flip.
Yeah.
That's
It's
your
right.
maximum likelihood forward one. So why, I mean, the question is, why do you want to additionally do this flipping by times in one? Because Bradley already has one. Accommodates from that.
Bradley did accommodates a lot, but it assumes it will want only the preferences. So if you could prove the like bounds, preferences are true, right? If the original data set is
For two preferences, they are all stochastic.
yeah.
So there is obviously a small chance of things.
Yeah. So here we are telling that okay, we know the data is noisy, we're trying to model the noise. And we'll apply that Bradley theory on that.
Also, this splitting is independent of the XY stuff. This is, the epsilon doesn't change depending on
Yeah,
the line.
no, epsilon is fixed epsilon. But
Even if there is a very clear demarcation between y1 and y2, whatever, AW and
AW, yeah,
you are still insisting that they will flip with probably epsilon.
yeah.
Is that not?
Yeah, there might be the case in real data set, right? Some portion of the data set might be flipped with very high probability. But they are clear enough. But in here we are considering everything is same. Across. So our goal.
One question, can you correct me? What do you mean when you say Bradley bounds for noise directly?
So Bradley did elusive model with put probability right on the choices. So it will prefer AW over AL with some probability, not with probability 1. So it will always prefer, there is some probability, it will prefer AL over AL. Models that. It models random draws of a demand, right? We are telling humans sampling randomly from Bradley user model. And then there is some extra level of noise added because humans are probably not capable. Right? So there is some extra level of, suppose our expert human versus our novice human. We're assuming the expert human samples from the Bradley user model. However, the novice human, it first samples from a Bradley user model, but there is an extra level of noise because of this nonsense.
What do you mean is sampling from the Bradley user?
Sampling, so there is a distribution, right? So human will tell that okay, I prefer AW over AM with some problem. Right? So that's the sampling. So I prefer AW over AM from probably 0.8. I prefer AW over AM with probably 0.8. Suppose I'm an expert human, and probably that is the best one to do. However, there's a novice human, novice level, you can tell them okay, no, I'll do it for 0.6 and 0.6. So the 0.2 is the noise. So that's what we're trying. So our goal as usual is to learn a policy from this noisy data set D tilde that generates maximum average result. Alright. So how do we come up with our loss function under noisy preferences? Okay. So preference probability under random noise model is given by this equation. So probability of the observed noisy samples A tilde W is preferred over A tilde L. This is equal to probability of AW is preferred over AL. So while AW and AL are clean samples from in the data set, clean samples. There is no noise. And since this is a clean samples and we multiply it with probability of no flip. Now obviously there is a probability of AL is preferred over AW, some probability. And then we will multiply it with probability of the flip. So this is probability of total probability.
Can you clarify what you mean by the clean and the
So A tilde W is observed data set, right? A tilde W and A tilde L, the observed data set that we are observing. Okay, this is the chosen, this is the rejected. But actually, AW is the chosen, A is the rejected. Actually, that is a true clean data.
how are you getting that? Are you getting that or are you?
We are not getting that. We are only observing A tilde W and A tilde L. We are modeling. So there is a clean preference choice, which is AW is greater than good. But obviously, under Bradley theory, there is some probability of this, some probability of the opposite theory. So this is the correct one. A tilde AW is greater than AL. So we have to multiply with probability of no flip. And this is the wrong one. AL is greater than AW. We multiply with probability of flip. So in that way, we get the probability of A tilde W is greater than A tilde L. These are the observed samples. So the first approach which comes to mind, okay, we have this probability of A tilde W is greater than A tilde L. We just minimize the negative log likelihood of this probability and solve some put out of MLE and get the solution. And as I talked about, there is a cDPO, the heuristic, which does the same thing or a variation of this kind of approach. They compute these probabilities and do maximum MLE estimation. However, this naive, as we have shown in the experiment, this naive MLE doesn't work. So why this doesn't work? So as we can compute the log odd, or the log odd means log of p by 1 minus log odd of p is log of p by 1 minus p. The log odd of this preference probability of observed samples, right? this observed noisy preferences. The log out of this is not equal to log out of preference probability of clean and correct preferences. These are completely, this doesn't equal. So that's how the noise are not completely eliminated from the algorithm. Now, as you can all guess, we want a loss which have this to be equal, right? So which loss gets us this? Turns out the following probabilities are normal. This I am calling probability, but this has some kind of unnormalized probabilities. Satisfy this. So we have p hat. This p hat will construct some p hat, which will construct p hat using this equation. So here, right, we did 1 minus epsilon times p plus epsilon times p of AW greater than AL plus epsilon times p of AL greater than AW. Instead of the plus, we'll do the minus. So we'll do some slight modification, and also we'll take the log. There is no log here. We'll take the log, and basically we'll compute p hat using this equation. We know log of p. We know this probability by this equation. We know probability by this equation. We'll compute this, and we'll assume we know epsilon. So this probabilities, the unnormalized probabilities, has this property. The log out of p hat under noisy preferences is equal to log out of p under clean preferences. So this desired property is satisfied by this equation. So we want to do this and come up with a loss function. So here, okay, so we'll take our loss function L hat of epsilon, which is this kind of log of p hat that I have just shown, and we'll just divide it by some scaling factor. And it turns out it equals to this equation, which is 1 minus epsilon of the loss. This is the DPO loss that I have shown. Loss of A tilde W and AL minus epsilon times loss of A tilde L and A tilde W. So first loss actually prefers A tilde W over AL, and the second part prefers A tilde L over A tilde W. The first part, which actually we want loss function to do this, right? Prefer A tilde W over AL, A tilde L. So we multiply with probability of no field. However, the second part does the opposite thing. Prefer A tilde L over A tilde W, which you do not want. So we multiply with probability of epsilon. It turns out this p hat satisfies this relation. And what it actually do, this L hat of epsilon becomes an unbiased estimate of the original DPO loss. So take L hat of epsilon and take an expectation over the probabilities. Then you get back your DPO loss. So as you can see, so the effect of noise has been debiased by coming up with this p hat, making sure log outs are correct. Effect of noise has been debiased. And so this makes the loss robust to preferences. Okay, so now we have our loss L hat epsilon, and we take an empirical minimizer of this loss function from we have a dataset D tilde, which consists of this pair S A tilde W and tilde L. We take sample average and just find a policy which minimizes this loss. Okay, and this we call our worst DPO policy after n datasets for n collecting n samples. Pi at n is pi, which parameter? Parameter is by this parameter theta. This is the policy.
Question: the previous step, you just say direct MLE with this new noise model. That
Which one? Yeah, previous direct MLE with this one.
with the two-step noise.
Exactly. Previous this one.
Yeah, so if you just do direct MLE with that, then there is some issue.
Then there is some issue.
And
Then now come up with a
proposing a different loss function.
different loss function. This new p hat. Come up with a new p hat. We're proposing a new robust loss function.
And this does it have an interpretation as some kind of MLE or no?
No, this is not MLE. This just have the log probability.
So mixture in the logwards,
Yeah,
logwards space. So it doesn't have
Mixture, yeah, exactly. Mixture and
mixture in the logwards.
Yeah.
So how are you sure that your particular loss function is working? Because it's
working.
logwards equal to-
Yeah, that's the hunch. That's the guess. I don't know. First, I have to take it empirically, and I can prove some bound for this one, not for the MLE one. I can prove some bound for this one, not for the MLE. sorry, I can prove bound for the MLE one, but that bound is worse than our. That also works. That will also convert, but rate will be worse.
So is there some parallel of this kind of idea for robust like standard regression, heuristic regression?
In terms of this loss, right? This kind of loss has been calculated using classification literature.
Okay, that's what I was asking.
Yeah, this has been done in classification. Some kind of classification literature. This has been done.
And it is known to be robust.
Yeah, no people. Yeah, but they bound the generalization errors. But while in our case, the bounds are different because there is nothing called generalization error. You have to bound the performance of the policy.
Also, is the proof of the red underlying thing, is that like very simple or?
It's a one line proof.
It's one line?
Yeah. So yeah, it's a one line. Okay. So I am now claiming DPO is robust. I have given you a robust DPO policy. Now I'll just prove my point. Try to prove my point by showing this experiment. Okay, this is a task. It's a sentiment generation task using IMD dataset.
So in the red line you have taken, so is it because of the noise you are considering is also zero mean? Does that something has to do with that or
Noise is not zero mean. Noise is epsilon. Mean of the noise is epsilon. It's a binary randomness.
thank you.
Alright, so now I'll try to give some results. Okay. So task is given a prefix of a movie review from IMDb dataset. Generate a review with positive sentiment. Okay, that is the task of the policy. So we run the RLHF or DPO pipeline. Stage 1, GPT-2, our effective policy. Stage 2, okay, in that dataset there is no pairwise comparison. So we'll use GPT-4 to collect pairwise comparison data. That means we generate answers and ask GPT-4 to give pairwise comparisons. And using this comparison data, we fine tune the effective policy using DPO or RLHF, whatever thing you want. Okay. So, and how do we evaluate the policy? We generate reviews using final policy and ask GPT-4 to give us score of that review. This is our evaluation study. Okay, so we first run the clean data set. This is all clean data set, no noise is here. Okay, we run DPO. So the DPO, the vanilla DPO, will get this kind of 0.99% of accuracy on this clean data set. We can also run vanilla RLHF and get this 99% accuracy. However, as we introduce some noise in stage 2, so what we do, we flip the 40% of the preferences. Take the whatever we have generated, flip 40% of the data. So now we run DPO on this noisy data. As we can see, the performance of degraded substantially, 88% now is the accuracy, whereas PPO is also degraded, right? So DPO is not working with the noisy data. Now we run our algorithm rDPO, robust DPO, we get back the in exactly same numbers. So since this is a semi-synthetic experiment, we introduce all the noise and we know the preferred true noise levels. So you can see the robustness effect coming out here. However, we also run the heuristics that have been proposed in the literature. This you can see that this is the MLE approach. That is also not doing good. So there is the empirical proof that this is robust, that this is not. So similar kind of things we can do for RLHF also, and similar kind of results. Not obviously we are not able to match 0.98, but similar kind of results follows. So the conclusion is our approach rDPO and rPPO are robust to preference. All right. So let me now explain why this is happening. Why we are doing good. So for that we need to do an anatomy of the gradient of the loss function. So theta, so the gradient updates for DPO family of algorithms. So DPO, cDPO, rDPO, for all the algorithms, gradient updates look like this. So there are two cases. So there is when there is no flip, right? Take the data sets, take the data points when there is no flip, right? Where flipping is random. So take the data point where there is no flip. So gradients are like theta equal theta is theta plus some constants, del theta of this, right? And this thing. And when there is flip, the gradient is like this. So let me explain. All right, in the first case, no flip. The first term, what it does, it increases the log likelihood of the preferred answer, the chosen response. And the second term with the negative minus in the front, it decreases the likelihood of rejected response, which we want, right? We want to increase the likelihood of chosen, we want to decrease the likelihood of rejected, which is one. And this is for no flip. For no flip, we are good. Whatever we want, it's happening in the gradients. However, when there is flip, right? Now see the flip, this you can think this term, like this whole term in the brackets, right? This is the direction of the gradient, right? So what it does, it increases the likelihood of the rejected response, right? So pi theta of AL, increase the likelihood of the rejected response. It also decreases the likelihood of the chosen response. Both we do not want. So whenever there is flip, we do not want any of this, right? But it's happening, we cannot control. So this is the gradient update of all the DPO family of like DPO, CDPO, rDPO, everyone. This is what we see. Only all the algorithms differ in the weights. There's some zeta sitting in front of the gradients. All the algorithms differ in the weights. For example, this weights, gradient weights of rDPO is gradient weights of DPO plus something epsilon by 1 minus 2 epsilon. This is a positive quantity. So same. So gradient weights of rDPO is higher than gradient weights of DPO. Similar thing for CDPO also. So what does this mean? The robust DPO updates are aggressive. It's always gradient weights are always higher. Be it under flip, be it under no flip. Always higher. Both in the correct direction, where no flip is the correct direction. Also, it is aggressive in the incorrect direction when there is a flip. We want this thing. Obviously, we want it to be aggressive in the correct direction, but we do not want it to be aggressive in the incorrect direction. But we cannot help it. It is happening. But how? But why it is working?
Beta is same for the from DPO, right?
Beta is that KL divergence
Correct,
concept. Yeah,
that is
that's
from
the
the DPO.
One question, why in the flip case, this is what the parameter update equation is?
Yeah, if you calculate the gradients, it goes down like that. If you calculate the gradients, you will get it. Just this thing will get flipped, nothing else. So you can go to the there's a link share, you can go to the paper. Why this thing working, right? Right? So the catch is probability of flip is less than 0.5. Yeah, done. Yeah, almost done. Probability of flip is less than 0.5, right? So with higher probability we are good. With lower probability we are bad. That's why things work. So robust DPO updates move in correct direction faster than DPO because of probability of flip is less than 0.5. If probability of flip is greater than 0.5, nothing will be done. So that is the catch. All right. Okay. So I promise that gives the some convergent bound. So let's just take a very quick 1 minute to consider neural network policy given by this equation. You can think of some kind of softmax thing. F theta, your F is your neural network architecture. Theta are the weights. We'll assume F theta is bounded. It is Lipschitz. It is twice differentiable. And gradients are also Lipschitz. All these assumptions we put for bounds. In this slide, I will show results for log linear policies, but that means I'll assume F theta is linear. I'll make further assumption. F theta is a linear function of theta, but phi is the feature vectors. However, we'll get similar kind of results, although Watt's results holds for neural network policies with this assumption. Okay, so this is the sub-optimality gap of our rDPO policy from the optimal policy. Okay, pi hat n is our policy, pi star is the optimal policy. We solve this equation. The bounds are given by this complicated equation. This is the order of this thing. So we'll explain these 1 or 2 important terms. One term is kappa. Kappa is a relative condition number between feature covariance matrices. So features are this. Take this feature vectors and compute covariance matrix. You can do it, right? Feature vectors just 5 transpose. We'll do the expectation. And sigma pi is basically expectation of 5 transpose where A is drawn from pi. And sigma pi SFT is same thing where A is drawn from pi. So compute this covariance matrices and compute the condition number lambda max of sigma pi divided by lambda min of sigma pi SFT. And this is the kappa. So it depends on kappa. Like this. So what does this mean, right? Why? What does this mean? This means that we need a SFT policy which is good enough. If SFT policy is lambda mean of sigma pi SFT is 0, right? Then these bounds blow up to infinity. So you need a SFT policy which is good enough, which covers the feature space well enough so that lambda mean is greater than 0. So as also evidenced by practitioners, DPO needs a good enough starting SFT policy to work. So this is captured in the bounds. Why you need that? There's another important term which is gamma. Gamma is nothing but lower bound on the first derivative of the sigmoid function. Sigmoid is a log in the log of sigmoid, that is the loss. It's a lower bound on the first derivative. This is also a very prohibitive term. So this and the bounds are square root d over n. N is the number of data points. So if we increase number of data points, policy will converge. And where d is the parameter dimension, that is a complexity. And the dependence of noise is 1 minus 2 over epsilon. So now I've told that okay, we can do proof for DPOs. For DPO, when there are no noise in the data set, assuming there is no noise in the data set, just put epsilon equal to 0 in the above equation, you get the bound, and that is the convergence bound for the DPOs. It's a byproduct of this analysis. So yeah, the one open question, if I want to pinpoint one, there are several open questions. If I want to pinpoint one theoretical open question, this 1 by gamma can be exponential in norm of theta and k penalty term beta. Like, you do not know what is the exact term or how to do this. Is there a better way of analysis? So it's one theoretical question.
Any lower bounds?
No lower. So yeah, I talk about I'll just give one couple of pointers. I talk about this one, quality of data, but there can be different issues in human preference data. One can be quality, noise in the data set. So this is the work I talked about. One can think about also how to quantify the amount of data needed to train a good policy, right? Because collecting huge volume of preferences from labelers can compromise the quality. Right? Suppose you hire a labeler and give some 10,000 or 1 lakh examples and give them some budget to do it, they might do some very quick job, right? You might not need this amount of data. So how to quantify this? Also, since we are recruiting labelers and asking them to give preferences, privacy of the data also becomes a very important issue. So how to train RLHF or DPO using making the private information of the data of the labelers protected. Right? So these 3 lines of the parallel work I'm doing, and I'm mainly interested in this kind of work. So this paper to be is the archive link, paper to be presented in this workshop. And I'm looking for solutions because the initial work, a lot of open-ended things, suggestions, collaborations, okay, questions.
Thank you, sir, for the informative talk. And we have arranged a refreshment at the coffee hut. So you can continue a conversation with Sayak if you were interested. Thank you.
We take questions there.